Today we shall be discussing about image impedance, iterative impedance and finally the characteristic impedance of a two port network, characteristic impedance of a two port network. Now, let us consider a general network having impedances ZA, ZB and ZC. The ports are 1 and 2. Now, image impedance we define image impedance as this. If I load this side by an impedance ZI2, the impedance seen from this side is ZI1, and if I load this same network, I show the network just by a block. If on this side if I put ZI1, then impedance seen from this side is ZI2. Then ZI1 and ZI2 will be the image impedances for this network. So, for a general network where ZA, ZB, ZC are any set of values, ZI1 and ZI2 will be different. So, there are two image impedances. You look into the circuit from this end, if I load on that side ZI2, then the impedance in is ZI1. If I look at the network from this end and if I load it with ZI1, the impedance in is ZI2. Mind you, you cannot have these unique values with any set, you cannot have any combination. So, they are dependent on, these values are dependent on ZA, ZB and ZC. Let us see what will be the relation between ZI1, ZI2 and these element values ZA, ZB and ZC. Now, by definition we have got ZI1, the impedance seen from this side is how much? ZA plus parallel combination of ZC and ZB plus ZI2. ZC in parallel with ZB plus ZI2, agreed. So, that gives me ZA plus ZC into ZB plus ZI2 divided by ZC plus ZB plus ZI2, agreed. Similarly, ZI2 will be equal to ZB plus ZC into, just replace A by B, interchange A and B, ZC will be ZA plus ZI1 divided by ZC plus ZA plus ZI1, agreed. So, if I cross multiply ZC plus ZB plus ZI2, if I bring on to the left side, what do I get? ZI1 ZI1 into ZA plus ZB plus ZI2 ZA plus ZB. If you add this, it becomes ZA plus ZB plus ZI2 into ZI1, and this side you will get ZA, ZC plus ZB plus ZI2 plus ZC into ZB plus ZI2. Correct me if I am wrong. Let us see, ZI1 into ZC plus ZB, ZI1 into ZI1, ZI2, ZI1, ZC, ZI1, ZB. So, actually this one has been written here first, and similarly ZI2 into ZA plus ZB plus ZI1 equal to ZB, ZB into ZC plus ZA plus ZI1 plus ZC into ZA plus ZI1. So, from this you can write ZI1 ZI2 minus ZI1 into ZB plus ZC plus ZI2 into ZC plus ZA minus, I can write sigma ZA ZB, which means ZA ZB, ZB ZC plus ZC ZA. So, I am writing in a compact form equal to 0. Let me call it equation number 1. Similarly, from the other one we will get ZI1, ZI2 plus ZI1, ZI2 plus ZI1 into ZB plus ZC minus ZI2 into ZC plus ZA plus sigma ZA ZB equal to 0. It is so simple. So, can you see, you can manipulate these by adding and subtracting, this will be minus sigma ZA ZB equal to 0. So, if I add these two, what do I get? Twice ZI1 ZI2, ZI1 into ZB plus ZC plus ZI1 into ZB plus ZC. So, this will get cancelled. Similarly, this will get cancelled. So, I will get twice ZI1 ZI2 equal to twice sigma ZA ZB, or ZI1 ZI2 equal to sigma ZA ZB. Similarly, subtracting 2 from 1 will eliminate these two. So, what do I get? By subtracting, I get ZI1 into ZC plus ZB equal to ZI2 into ZC plus ZA, or ZI1 by ZI2 equal to ZA plus ZC divided by ZC plus ZB. So, from 3 and 4, if I take the product, I will get ZI1 squared as ZA plus ZC by ZB plus ZC into sigma ZA ZB. Therefore, ZI1 is square root of ZA plus ZC by ZB plus ZC into sigma ZA ZB. It is so simple. So, you can see from here ZI2, if you just look into the circuit from the other end, it is just replacing A by B. So, it will be ZB plus ZC by ZA plus ZC into sigma ZA ZB. Agreed? So, these are the two impedances. Now, if you are having say ZA equal to ZB, ZA equal to ZB, then what do I get? If ZA is equal to ZB, if ZA is equal to ZB, then it becomes a symmetric network. So, for a symmetric network, here if I put ZA equal to ZB, this will get cancelled, this will be 1, and sigma ZA ZB will be, therefore, ZI1 is equal to ZI2 will be square root of sigma ZA ZB, which is square root of ZA ZC plus ZA ZC plus ZA squared, that is ZA squared plus twice ZA ZC. Okay. Now, can you find out for an asymmetrical L network what will be the image impedances for an L network? L network means, suppose you are having this network, what will be for an L section, what will be the image impedances? You are given ZB equal to 0. So, put ZB equal to 0 here, what do I get? ZI1 will be ZA plus ZC by ZC and what will be ZA ZB, these terms only ZA ZC, because ZC into 0 is 0, ZA into 0 is 0. So, multiplied by ZA ZC, which finally gives me ZA squared plus ZA ZC. Sorry, excuse me. What will be ZI2? ZI2, if I put ZB equal to 0 is ZC by ZA plus ZC. So, it will be ZC by ZA plus ZC into ZA ZC, which means ZC into ZA, I can multiply by ZA and also multiply ZA here in the denominator. So, this will be ZA square plus ZA ZC under root. Is that all right? So, this will be the expression for ZI2, this will be the expression for ZI2, and Zi1 is this much for an L section. Now, let us define an iterative impedance. What do you mean by an iterative impedance for a network like this? Once again, we will take a T section ZA, ZB, ZC. By iterative impedance, we mean if I terminate this side by say ZT1, then impedance seen from this side is also ZT1. Again, if I terminate this side by ZT2, then impedance seen from this side is ZT2. So, ZT1 and ZT2 are the two iterative impedances. Mind you, you cannot truncate it, you cannot terminate this by any impedance and see from this end the same impedance value. There is a particular impedance by which you can terminate and you can observe from this end the same impedance value. So, what is that particular impedance ZT1? Similarly, for ZT2, what are these two impedance values? Okay. So, now we will be taking, say, we may say, if I replace, if I terminate this by 300 ohms, impedance seen from this side is also 300 ohms. If I terminate this side by 700 ohms, impedance seen from this side is also 700 ohms. Then this 300 and 700 are the two iterative impedance values for a given network. So, let us take once again from definition ZT1, impedance in is ZT1. So, ZT1 will be equal to ZA plus parallel combination of ZB plus ZT1 with ZC. Okay. So, ZT1 is equal to ZA plus parallel combination of ZC with ZB plus ZT1, which means ZA plus ZC into ZB plus ZT1 divided by ZC plus ZB plus ZT. If I multiply again, cross multiplication will give me ZT1 squared plus ZT1 into ZC plus ZB on this side. On this side I have got ZA ZC plus ZB plus ZA ZT1 plus ZC ZT1 plus ZC ZB. If I transform everything, if I transfer everything on this side, I will get ZT1 squared plus ZT1 into ZC plus ZB minus ZC minus ZA. So, it becomes ZB, ZC will go, so ZB minus ZA. Correct me if I am wrong. Okay. Minus ZA ZC ZA, ZC minus ZA, ZB minus ZC, ZB equal to 0, or I can put all of them as plus. Okay. That is ZT1 squared plus ZT1 into ZB minus ZA minus sigma ZAZB equal to 0. So, how much is ZT1? I can straight away solve this quadratic to get ZT1. ZT1 will be minus of B. So, ZA minus ZB plus minus root over of ZB minus ZA whole squared minus 4AC. So, minus and minus make it, will make it plus 4 sigma ZAZB divided by 2. Okay. So, this is the expression for ZT1. Now, can you write in a similar manner the expression for ZT2? Is very simple. Replace, interchange ZA and ZB. So, this will become ZB minus ZA. Now, plus minus, if I consider the minus value, you can see obviously this is a quantity which is larger than ZB minus ZA, all right. So, you are extracting a quantity which is more than this. So, it will be giving you negative values of ZT. So, that negative solution is ruled out. So, we will consider only the plus value. Okay. So, similarly, this one will be ZB minus ZA whole squared plus 4 sigma ZA ZB. If we have an L section, that means a section like this, what will be, this is ZA, this is ZC, what will be ZT1 and ZT2? Just put ZB equal to 0. So, that will give me ZT1 equal to half of ZA plus root over of ZA squared plus 4 into ZA ZC, ZB 0. So, ZA, ZB, ZB, ZC, ZC, ZA, that will give you just ZC, ZA, and ZT2 will be half of ZB minus ZA. So, minus ZA plus root over of ZA squared plus 4 ZA ZC. Okay. Now, if you have a symmetric network, for a symmetric network, ZA equal to ZB. So, what you get? If ZA is equal to ZB, then this will be 0 or this will be 0, this will be 0. So, it is square root of 4 sigma this and half, 4 and half will get cancelled. So, it will be sigma ZT1 equal to ZT2 equal to sigma ZA ZC plus 2 times ZAZC plus ZA squared. Sigma ZA ZB becomes ZA square, ZA into ZA plus ZA into ZC plus ZA into ZC. So, that gives me this, which is nothing but ZI1 or ZI2. We call this, that is for a symmetrical network, the image impedance and the iterative impedance will be identical, and that will call as characteristic impedance. Some people write ZO, some people write ZC. So, the characteristic impedance refers to a symmetric network, and that is equal to ZA squared plus twice ZAZC under root. You can also find out the image and iterative impedances for a pi network. That is also a very interesting derivation for a pi network. If we consider YA, YB and YC, then what would be ZI1 and ZI2? You can see for yourself, any pi network can be converted to an equivalent T network and you can derive it, or straight away from definition. Suppose this is terminated by ZI2 and impedance in is ZI1. So, go from the definition, ZI1 is equal to this admittance plus this total admittance. If you invert, that will be giving you ZI1. So, ZI1 can be written as 1 by YA plus admittance of this, which is 1 by impedance YC, how much is it? 1 by YC plus 1 by YB plus ZI2. So, this impedance is ZI2 plus, so sorry, 1 by ZI2, admittances are to be added, sorry, I will write here separately. ZI1 is 1 over the admittance YA admittances you add YA plus this admittance, and what is this admittance? It is 1 by this impedance. What is this impedance? 1 by YC, is it not? This whole thing I am conceiving as an impedance, and what is this impedance? This admittance plus this admittance, that is YB plus 1 over ZI2 is this admittance. So, inverse of that is the impedance. This is to be added with this impedance, which is 1 by YC. So, this total impedance, if I take the inverse of that, that becomes the admittance. So, it will be 1 by YC plus 1 by YB plus 1 by ZI2. Now, you can simplify this. Zi2 divided by Yb Zi2 plus 1 and so on. You can simplify and then finally you get a relationship between Zi1 and Zi2 for the impedance seen from this side. Similarly, impedance seen from this side, you establish a relation between Zi1 and Zi2, and in the same manner you can evaluate Zi1 and Zi2. One interesting relation is you can verify for yourself Zi1. Let us go back to once again a T network. If I perform from this end an open circuit and short circuit test, that is, keep this open Z, Zc and Zb. So, Z open circuit seen from this side, how much is it? Za plus Zc. Okay. Short circuit this seen from this side 1 1 dash. If I short circuit it, how much is it? Za plus Zb Zc by Zb plus Zc, agreed, which means Za Zb plus Za Zc plus Zb Zc. So, sigma Za Zb divided by Zb plus Zc. If I take the product, Z open circuit 1 into Z short circuit 1, okay, how much is it? How much is it? If I multiply by this, it is, and then take the square root Za plus Zc divided by Zb plus Zc into sigma Za Zb, is it not? Z open circuit and Z short circuit seen from the same terminal pair gives me this product, and then if I take the square root, what is this? You can identify this as Zt1, sorry, Zi1. Similarly, seen from this side, it will be Zb plus Zc by Za plus Zc. So, that will give me Zi2. So, Zi1 is Z open circuit 1 into Z short circuit 1. Zi2 is Z open circuit 2 and Z short circuit 2. This is a very interesting result. And for a symmetric network, Z characteristic equation, characteristic impedance Z0, which is Zi, that will be equal to Z open circuit into Z short circuit, because ZOC1 and ZOC2 they become same for a symmetric network. Okay. Let us consider some simple values. Say this is 200, this is 400 and this is 600. What will be Zi1, Zi2, Zt1 and Zt2? Okay. So, we have got Za equal to 200, Zb equal to 400 and Zc is equal to 600. So, ZI1 will be equal to root over of ZA plus ZC 600 plus 200 800 divided by 600 plus 400 1000 into sigma ZAZ will be 200 into 600, 6 2s are 12, 6 4s are 24 plus 4 2s are 8 into 10 to the power 4. Do you agree? So, that gives me 0.8 into 12 plus 24. So, 12 plus 8 20 plus 20 into 44 into 10 to the power 4. Do you agree? So, that is approximately 35.2 44 into 0.8 into 10 to the power 4. So, 35.2 is approximately say 59, 5.9 into 10 to the power 2. So, 590 ohms approximately. Similarly, ZI2 will be just these two figures will interchange. So, 10 by 8 which means 1.25 into 44 into 10 to the power 4, which means approximately 44. If I assume this to be 11, so it will be 220 11 44 into 1.25. So, that gives me 5 by 4. So, 55 square root of 55 is say 7.3 or 7.2. So, 720 ohms. So, these are the two values of ZI1 and ZI2. If you ask me what will be the iterative impedances ZT1 and ZT2. So, ZT1, if you just substitute these values in ZT1 and ZT2, how much did we get? ZT1 was half of ZA minus ZB plus root over ZB difference ZA whole squared sorry plus 4 sigma ZA ZB. So, how much will it come to? Half ZA, that was 200 minus 400 plus root over of 200 minus 400. So, 200 squared plus 4 into ZA ZB, ZB ZC plus ZC ZA, that was 44 into 10 to the power 4. So, half of minus 200 plus, I can always take 10 to the power 2 outside, inside I am left with 2 2s are 4 plus 4 into 44 176. Correct me if I am wrong. So, that is half minus 200 plus 176 plus 4 180. Is that all right? 200 squared 10 to the power 4. So, 176 180, square root of 180 is 13.5, say 13.4 into 10 to the power 2. So, that is this is an approximate figure, minus 100 plus 680, say 670. So, that is 570, and ZT2 is everything is same except that ZA and ZB will be just interchanging their position. So, it will be instead of minus 200 it will be plus 200. So, it will be 100 plus 670. So, that is 770. So, these are the two values for ZT1 and ZT2. If I have ZA equal to ZB, say 200, 200 and 600. If ZA equal to ZB equal to say 200 and ZC equal to 600, then you have got a network like this. What will be the characteristic impedance? This is 200, this is 200, this is 600. You can either put those values here in the expressions, or you can apply short circuit and open circuit test directly. So, root over of, if I have an open circuit test, it is 600 plus 200, 800, and if I apply a short circuit test, 200 plus parallel combination of 200 and 600. So, it will be how much is 200 into 600 by this plus this is 800. So, zeros will go, 6 to 1200 by 800, 1200 by 8, so 150. So, 800 into 150 square root of that. Okay. So, 1, 2, 3, 4. So, 8 into 1.5 is root over of 12 into 100. That is approximately 34.5. So, 345. So, in that case the characteristic impedance is calculated directly from the short circuit and open circuit test. You can also substitute the values in the general expression. Okay. Thank you very much. We shall continue with this in the next class, and then we will go into the calculation of propagation constant. Thank you very much. Sorry, we forgot to include this 200 ohms resistance here. Actually, this was 600, this was 200 and this was 200. So, the short circuit impedance as seen from this side would be 200 plus 150. So, it should be 350. So, Z characteristic equation, characteristic impedance will be 350 into 800, and that is approximately 530 ohms and not 345. I am extremely sorry, please make this correction. Now, suppose we have a question. Suppose you are given Z open circuit 1, Z short circuit 1 and Z short circuit 2. These three values are given. Can you determine ZA, ZB and ZC? It is very simple. Here you can see the network is like this: ZA, ZB and ZC. So, if you are measuring the short circuit impedance, say open circuit impedance, then ZA plus ZC is equal to ZOC1. Similarly, ZA plus ZB ZC parallel combination, ZB into ZC by ZB plus ZC, that is equal to Z short circuit 1. Similarly, seen from this side, ZB plus ZAZC parallel combination, ZAZC by ZA plus ZC. This is a parallel combination of Z and ZC. So, that is equal to Z short circuit 2. So, from these three given conditions you have to determine Z A, Z B and Z C. So, one can solve like this: Z B plus Z C equal to, you can verify for yourself, Z short circuit 2 by Z short circuit 1. Okay. Z short circuit 2 by Z short circuit 1, that will be, see the numerator is Z A Z B, Z B Z C, Z C Z A. So, that will get cancelled. So, Z A plus Z C and Z B plus Z C, these two will be involved here, and then one Z A plus Z C will get cancelled here. So, this product will give me this, say Z dashed, and then Z A plus Z C is known, that is Z O C 1. So, you can evaluate from here Z C, if you can, little bit of manipulation will give you Z C equal to Z O C 1 squared into Z S C 2 by Z S C 1 minus Z O C 1 into Z S C 2. Now, I leave it to you to compute and verify this relation. It is very simple. It is a question of only elimination of the terms Z. I can take common Z O C 1, Z S C 2. So, I am left with Z S C 1 by Z O C 1 by Z S C 1 minus 1, under root of this into under root of this. So, therefore, Z A can be evaluated Z O C 1 minus Z C, which is computed from here. Similarly, Z B is Z dashed, which you have already computed, minus Z C. So, this is how you can compute Z A, Z B and Z C. Now, suppose you are given a lattice network. What is a lattice network? It is like this: you are having a bridge network like this. This is Z A, Z B, Z B, Z A, and you are having the output terminals here 2, 2 dashed, 1, 1 dashed. Okay. So, this can be also shown as Z A, Z B, Z A and Z B. These are the output terminals. This is Z B. Quite often we show this as Z A, Z B, and the rest of it is shown by dotted line. That means, this is Z A and this is Z B, it is repeated. So, this is also a standard notation for a lattice network. What will be Z naught for this kind of a network? Now, Z naught, as you know, is equal to Z open circuit into Z short circuit. It is a symmetric network. So, whether you look from this side or that side, Z O C 1 and Z S C 1, they will be equal to Z O C 2 and Z S C 2. So, how much is Z open circuit? If I keep it open, it is Z A plus Z B and again Z A plus Z B in parallel. So, it will be Z A plus Z B by 2, is it not? Two identical impedances in parallel. So, that will be effective impedance will be half of that. And what will be the short circuit impedance? If I short, it is Z A and Z B in parallel, once again Z A and Z B in parallel. So, it will be 2 times parallel combination of ZA ZB, which will be ZA ZB by ZA plus ZB. So, under root of this. So, 2 will get cancelled, ZA plus ZB will get cancelled. So, this will be ZA into ZB. Is that okay? So, this will be the characteristic impedance. Now, if you look back, what will be the propagation constant? What will be the ratio of the currents IS and IR? Now, once again I will take this diagram. Suppose this is IS, and when I put an impedance Z0 here, this the current through this impedance is IR. Okay. Let this current be I1, then the current through this is IS minus I1, is it not? And this current is IR, this gets added with this. So, this final current will be IR plus IS minus I1. Okay. Now, what will be the voltage drop? If you look at the voltage here, Vs is equal to this total drop. Now, let us compute the drops. It will be I1 into ZA. So, I can write I1 into ZA plus IR into Z0, plus ZA into this current plus this current, IR plus IS minus I1. So, IR plus IS minus I1. This entire drop will be equal to Vs. Okay. So, we can write IR into Z0 plus ZA, plus IS into ZA, and I1 ZA will get cancelled with this I1 ZA equal to Vs. And what is Vs? Vs is again Is into Z0, the impedance in from this side. So, Is into Z0. Do you all agree? Therefore, if I transfer this to this side, IR into Z0 plus ZA is equal to Is into Z0 minus ZA. So, that gives me Is by IR as equal to ZA plus Z0 divided by Z0 minus ZA. Okay. So, the propagation constant, which was log of Is by IR, will be equal to log of Z0 plus ZA by Z0 minus ZA, which means e to the power p is equal to Z0 plus ZA by Z0 minus ZA, and that is equal to, that gives me, if I take componendo dividendo, e to the power p plus 1 by e to the power p minus 1 is equal to Z0 by ZA. And what is this? This is nothing but cot hyperbolic p by 2. If I invert it, so that will be giving me tan hyperbolic p by 2 is equal to ZA by Z0, or tan hyperbolic p by 2 is ZA by Z0. Z0 is equal to root over of ZA into ZB. So, that gives me root over of ZA by ZB. Okay. So, we get ZA is equal to Z0 tan hyperbolic p by 2, one may write like this, and ZB equal to cot hyperbolic p by 2. Either way you can write. all right. Okay, we will stop here for today. We will take up some problems in the next class. Thank you very much. Last time we were discussing about the image impedances and iterative impedances, and we derived these relations for a T network, that was ZA plus ZC by ZB plus ZC into sigma ZA ZB. This means combination of two impedances at a time. So, it was a structure like this: ZA, ZC, and this was ZB. Similarly, ZI2 we derived as ZB plus ZC divided by ZA plus ZC into sigma ZA ZB. This we derived last time. We also derived for the iterative impedances ZT1 as half of ZA minus ZB plus under root ZA minus ZB whole squared plus 4 times that sigma term ZA ZB. Similarly, ZT2 was half ZB minus ZA plus ZA minus ZB whole squared, the same expression. Okay. Then we discussed about a network that is a lattice network where we considered ZA, ZB, ZA, this was the notation, for the counterparts. This is ZB and this is ZA. This can also be seen as a bridge network like this. This was say